You ever just pause like mid-sentence and think about how absolutely wild language is? How we just make these sounds and bam, thoughts, feelings, complex ideas just jump from my brain to yours.
It feels so effortless, doesn't it? Almost like breathing.
Totally. But underneath all that easy chat, there's this incredibly deep, complex story unfolding. How did we even get this ability? And how is it still changing, like right now?
It really is a profound journey when you start digging in. I mean, we're talking about a path that stretches way back from maybe, the simple calls of our primate ancestors,
Right.
all the way to the incredibly complex, flexible communication we have today. And what gets me is it's not just linguistics, right?
Yeah.
It's tangled up with our biology, our brains, the whole evolutionary shebang.
That's exactly it. So for this deep dive, that's our mission. We're going to peel back those layers. We'll look at the physical changes, the stuff our bodies actually did to make speech possible, and the brain's role, which is just huge. And even how grammar itself, the rules of language, they're not fixed. They're evolving, often totally under the radar.
Yeah, you'll definitely have a new appreciation for like every single word after this.
Hope so.
And we're drawing on some really fascinating stuff here. Cutting-edge research. There are these studies applying ideas from, get this, population genetics.
Wow, like gene evolution.
Exactly.
Yeah.
Applying that thinking to how language changes, and also these great comparative reviews, looking at speech across different animals. It sheds amazing new light on some really old debates.
Okay, let's dive in then. And right off the bat, there's a really key distinction we need to make. It trips people up all the time. We throw around language and speech like they're the same thing. Interchangeable. But for understanding how this all evolved, they're pretty different beasts. And mixing them up really muddies the water.
Yeah, that's absolutely critical. So think of language as the big picture. The conceptual system itself. It's the code, the framework in our minds for handling complex ideas, abstract thoughts.
The mental architecture.
Exactly. And crucially, this system, it doesn't actually need sound. It can work in different ways, different modalities.
Feels like sign language.
Perfect example.
Yeah.
American Sign Language, Auslan in Australia. These are complete, rich languages. Grammar, syntax, everything. Just visual, not auditory. Or even written language. It's language just represented visually. So language is the underlying system.
Got it. So if language is the system, the meaning, the code, then speech is more the how, the delivery mechanism, basically.
Pretty much. It's the specific way humans usually convey that language system using sound. It involves all that incredibly complex coordination. Your breathing, your larynx, tongue, lips, making sounds.
And then hearing them, decoding them.
Right. Producing and perceiving sound. That's speech, the physical act.
Okay, that makes sense. System versus delivery.
And keeping that distinction is vital for looking at evolution.
Yeah.
Because, yeah, they're totally intertwined for us now.
Seamlessly, usually.
Right. But the different parts, the mechanics, they could have evolved separately. Maybe speech mechanics came along for one reason, the language system developed for another, or on different timelines. They likely didn't just pop up together fully formed.
Which leads us nicely into how we even figure this stuff out, historically speaking. The comparative approach. Because, I mean, you can't dig up a fossil and hear it talk, can you?
Huh. No, sadly not. Speech doesn't fossilize. That's a major limitation of the fossil record here.
So we look at living things instead.
Exactly. Studying vocal behavior in living animals, especially our closest relatives like chimps and gorillas, is invaluable. We look for homologies. Those are traits we share because we got them from a common ancestor.
Like a family resemblance.
Precisely. If we see a basic vocal thing in both us and chimps, it's a good bet our common ancestor might have something similar. It gives us clues about the starting point.
But it's not just about our close family, is it? There's this other really cool idea, convergent evolution. That blows my mind a bit.
Oh, absolutely. That's where some of the most surprising insights come from. Convergent evolution is when similar traits pop up independently in totally different species.
Like wings on birds and bats.
Exactly. Or streamlined shapes in dolphins and sharks. Different origins, similar solutions to similar problems. Now apply that to vocal stuff. Think about complex vocal imitation, learning totally new sounds.
Which we're amazing at.
We are. But we also see it in songbirds, parrots, even seals and dolphins. Totally unrelated lineages.
Weird.
It is. But when you see that pattern, it suggests there's a really powerful reason, some strong adaptive pressure favoring that ability. It helps reveal the why. Why did vocal learning evolve?
So, connecting this back to the fossil issue, if speech doesn't fossilize and those bones people used to argue about.
Oh yeah, the hyoid bone shape, the hole for the tongue nerve, the angle of the skull base.
Right. If those turned out to be, well, kind of dead ends for figuring out when speech started.
It just really underlines why this comparative approach, looking at living animals, is so crucial. For years, so much debate, especially around Neanderthals and speech, hung on those iffy skeletal clues.
Led to a lot of arguments, I bet.
Huge debates, often inconclusive, sometimes contradictory. And it kind of distracted from these other, arguably more fruitful, ways of using living species to understand the how and why of the changes needed for speech. It shows you need that cross-disciplinary approach.
Okay, fascinating foundation. Let's build on that and get into the anatomy itself, the actual machinery for speech, particularly our vocal tract. We all kind of grew up hearing humans have this special setup, right? That's what lets us talk.
That's definitely been the standard story for ages. And it's true. The adult human larynx, the voice box, sits way lower in the throat compared to most mammals, including apes.
Okay.
And this creates what's called a two-tube vocal tract, sort of like an L shape. You've got the vertical tube in your throat, the pharynx, and the horizontal tube in your mouth, the oral cavity.
And why is that L shape such a big deal?
Acoustically, it's huge. That specific shape lets us create an incredibly wide range of distinct formant patterns.
Formants. Right, those are like the resonances.
Exactly, like changing the shape of a musical instrument to get different sounds. Formants are the natural resonant frequencies of your vocal tract. They're totally crucial for making all the different vowel sounds, especially. That clear difference between saying E and woo, that's your tongue changing the shape of those two tubes, altering the formant frequencies. And importantly, formants are separate from pitch. Pitch is from your vocal cords vibrating. Formants are from the shape of the tract. Gives us this massive phonetic toolkit.
It's weird to think about how we do that without even noticing.
It is. And developmentally, it's interesting too. Human babies start with a high larynx, like an ape's. Helps them breathe and swallow at the same time.
Protection.
Right. Then it drops down over the first few years, usually around the time they're starting to babble and talk. And then there's a second drop, just in males, at puberty, which deepens the voice.
Okay, so let's unpack that assumption then. The classic idea was low larynx, uniquely human, evolved for speech. Full stop.
That was the dogma for a long time. A key anatomical marker setting us apart as speakers.
But recent stuff throws a wrench in that, you're saying?
It really does. Some quite surprising findings. Using cineradiography, basically X-ray movies of animals vocalizing.
Cool.
Scientists saw that the vocal tracts of mammals like dogs, pigs, goats, even monkeys like cotton-top tamarins are way more flexible than we thought.
How so?
They can and do temporarily pull their larynx down when they make loud calls.
Really? Like mimicking our setup?
Kind of. They move towards that human-like two-tube configuration just temporarily.
Huh. So maybe that ability to lower the larynx isn't uniquely human after all.
It suggests that maybe the potential for a lowered larynx during vocalization is actually a much older, more widespread mammalian trait. A sort of built-in flexibility, not some brand new human invention for speech.
That is a big shift.
And here's where it gets really wild. The killer finding. Some other mammals actually have a permanently low larynx, just like adult humans.
Wait, who?
red deer, fallow deer, possibly lions, camels, even koalas.
Koalas, seriously.
Yeah. So this anatomical feature we thought was our special speech adaptation. It's not exclusively ours, which forces a big question.
If it wasn't just for speech, or maybe didn't even start for speech, then what was it for?
Exactly. And that leads us to this really elegant alternative idea, the size exaggeration hypothesis.
Okay, intriguing name. What's the theory?
It starts with a basic acoustic fact. Bigger animals with longer vocal tracts naturally produce lower formant frequencies. Remember, formants signal track length, separate from pitch.
Right, so bigger animal, deeper resonance sounds bigger. Makes sense.
It's an honest signal of size. But the hypothesis suggests that lowering the larynx evolves, maybe initially, as a way to cheat that signal.
Cheat? How?
By actively lengthening the vocal tract, either temporarily or permanently, an animal can lower its formant frequencies.
Making it sound bigger and more intimidating than it actually is.
Exactly. It's acoustic deception, like standing on your tiptoes vocally.
Huh. I like that. Are there examples?
Oh, yeah. Male red and fallow deer, during their mating season roars, they physically pull their larynx way down, sometimes even into their chest cavity.
Seriously?
Yeah, all to lower those formants and make their roar sound deeper, more threatening, exaggerating their size to rivals. And some birds do similar things, evolving super long, looped windpipes inside their bodies, again, just to lower their vocal resonances and sound bigger or more dominant.
Okay, now connect that back to us, that secondary drop in the male larynx at puberty.
Right. Think about it. It happens alongside other changes. Broader shoulders, facial hair, the voice deepening. It's all part of a package of traits that enhance a parent's size and maturity, often linked to sexual selection.
Making males seem more formidable or attractive.
Precisely. So the implication for our evolution is huge. Maybe the size exaggeration trick, the ability to sound bigger, was the original reason the larynx lowered in our ancestors.
A pre-adaptation, you called it.
Exactly, a pre-adaptation. It evolved for social signaling, maybe intimidation or attracting mates, but once the larynx was lowered for that reason.
It just happened to create this vocal tract shape that was also amazing for making lots of different sounds.
Bingo. The expanded range of formant patterns it enabled could then be co-opted, repurposed for this new function, speech.
So it wasn't designed for speech, but speech took advantage of it.
It offers a much more gradual, plausible evolutionary path. Evolution tinkering, finding new uses for existing parts, much more likely than a sudden, massive leap just for speech.
That makes so much more sense than just, boof, speech anatomy. Okay, so the plumbing changed, maybe initially for other reasons, but the plumbing alone isn't enough, right? You need control.
Absolutely. You need incredibly sophisticated brain control, precise, lightning-fast coordination of all those muscles. And this brings us to another big puzzle in language evolution, vocal imitation.
Our ability to copy sounds.
And not just copy, but learn and produce totally novel sound patterns. We are by far the champs at this. Learning new words, accents, singing, whistling.
Beatboxing.
Beatboxing. It's all vocal learning. And it's fundamental. Without it, how would we build up the massive vocabularies all human languages have?
Good point. You can't just inherit thousands of words genetically.
Right. Now, what's fascinating, truly striking, is the contrast with our closest relatives, the apes.
They can't do it.
Barely at all. Despite years of trying to teach them, apes show almost zero ability to learn new vocalizations outside their innate species calls. They can learn sign language, use symbols, but they can't learn to say new things.
But other animals can. You mentioned birds and dolphins earlier.
Exactly. It's this weird, patchy distribution. Songbirds are amazing mimics. Parrots can learn human words. Seals have been taught to mimic speech sounds. Dolphins and whales learn complex whistles and dialects from each other.
So it's not just a primate thing or even a mammal thing necessarily. It popped up independently all over the place.
Which makes you ask, why? What's the advantage? What was the original function?
Good question.
Well, one idea is about repertoire size. Maybe having a bigger, more complex song makes you more attractive to mates, like in birds, shows off your brain power or fitness. Or it could be for territory defense, the Beaugest hypothesis. You mimic lots of sounds. Maybe rivals think there are more individuals defending the territory than there really are.
The vocal bluff again.
Yeah.
Clever.
Yeah. Another idea, maybe more relevant to us social creatures, is signaling group membership or kinship.
Like having a secret handshake, but with sound.
Kind of. Think about dialects. Killer whales have distinct pod dialects passed down culturally. Dolphins has signature whistles. In social groups, knowing who's in and who's out is crucial. So maybe vocal learning evolved to learn the group's password, their specific accent or calls.
The password hypothesis.
Right. And this could create a runaway process. Groups demand slightly more complex passwords over time, driving selection for better vocal learning abilities. It could even explain human accents and how they mark social groups.
That feels very plausible for humans. Okay, so we've got the changing anatomy, possibly driven by size exaggeration, and this scattered but powerful ability for vocal learning. Now let's get into the brain itself, the controller. This is where Michael Arbib's work comes in, right? Computational neuroethology. Sounds fancy.
It sounds complex, but the core idea is brilliant. Arbib basically builds computational models of brain circuits to understand how complex behaviors could evolve step by step. He calls it conceptual neural evolution, using data from living animals to figure out how you could get from a simpler brain to a more complex one, like ours, incrementally, reverse engineering brain evolution.
And he uses these hypothetical computational preachers to map it out, starting simple.
Exactly. He starts with Rana Computrix, the computational frog.
Okay, ribbit.
Huh. This model looks at basic stuff. How a frog sees prey, targets it, snaps, how it avoids predators, how it navigates simple obstacles. The key idea is schemas, flexible units of perception and action, like a prey-catching schema. The model shows how these basic building blocks work and combine.
Building blocks. Okay, then he moves up.
To Ratus computator, the computational rat. Here, things get more complex, more mammalian. We see concepts like affordances, how the environment suggests actions. A ledge affords walking on, food affords eating. This involves the parietal cortex.
Yeah.
And action selection in the premotor cortex, choosing what to do. Plus, crucially, cognitive maps for navigation involving the hippocampus. The rat's building a mental model of its world.
Getting more sophisticated. And then the monkey. Macaca computrix. This feels like it's getting closer to us, especially the focus on hands.
That's right. The monkey model dives deep into controlling grasping movements, how the parietal cortex processes the graspability of an object and sends that info to premotor cortex, which holds the motor plans, the schemas, for actually making the grasp. That interaction is key.
And it's in studying the monkey's premotor cortex, specifically area F5, that they found something incredible, right? Mirror neurons.
Yes. This was a game-changer discovery in the 90s. Researchers in Italy found these specific neurons in area F5, and what was amazing was their dual function. They fired when the monkey performed an action like grasping a peanut.
Okay, motor neuron.
But they also fired when the monkey simply watched someone else, another monkey, or a human, perform that same grasping action.
Whoa. So the neuron mirrors the action it sees.
That's exactly why they're called neuroneurons. It's like the monkey's brain is simulating the observed action internally.
What are they thought to do for the monkey then?
Several things were posed. Maybe helping refine its own actions, comparing intended versus observed self-action. Maybe some simple imitation, though monkeys aren't great imitators overall. But a big one is understanding others' actions and intentions. Seeing a grasp, the mirror system activates, maybe helping predict what happens next. And Arbib's model suggests these neurons learn their properties by associating seeing their own hand move with the motor commands that moved it.
Okay. Now let's bridge this to humans and language. This feels like a potential missing link.
It really does. Because years of brain imaging studies, fMRI, PE scans, show that the human brain region considered homologous to monkey F5. Well, that's Broca's area.
The Broca's area, famous for speech production.
Very same. And guess what? Human Broca's area lights up not just during language tasks, but also when people observe or execute hand actions like grasping.
No way. So the language area is also an action area.
It seems deeply connected, which leads directly to the mirror system hypothesis for language evolution.
The proposes.
That the specialized function of Broca's area for language didn't just appear out of nowhere. It actually evolved from or built upon this older mirror system related to motor acts.
So our ability to talk might be grounded in our brain's ability to understand and perform physical actions.
That's the revolutionary idea. The mirror system gives you this basic capacity to link perception and action, to understand that an action you perform is equivalent to the same action performed by someone else. Arbib argues this provides the neural basis for language parity, the fundamental understanding that a word or sign means roughly the same thing for the producer and the receiver. It's the foundation for shared meaning.
Wow, that's a deep connection.
It suggests language readiness evolved gradually in our ancestors, building on these action understanding circuits. Complex grammar and syntax might have then developed more through cultural evolution, layering on top of this neural foundation.
And Arbib lays this out in stages, right? His 7 stages to language. It's not just one leap.
Exactly, it's a gradual climb. It starts with basic grasping, then a mirror system for grasping, then better imitation of grasping. First simple, then complex. That ability to imitate actions is key. From there, he proposes proto-sign, a communication system using manual gestures, but importantly, with an open repertoire. You could make new signs.
So language might have started with hands, not voices.
That's a core part of the hypothesis.
Yeah.
This manual system, built on the action mirror system, broke free from the limited, fixed calls of primates. Then comes proto-speech. The idea is the vocal system gets invaded or co-opted by signals from this hand-action communication system in F5 Broca's. The brain area controlling meaningful hand actions starts to control the voice in a more flexible, imitative way.
Vocal gestures become open-ended too.
Right. And finally, you get language as we know it, the jump to abstract grammar, syntax, recursion, a co-evolution of more complex thought and more complex linguistic structures. It's a beautiful incremental picture.
It really paints language not as a miracle, but as this amazing structure built piece by piece on older foundations. Incredible. Okay, so that's the deep history, the evolution of our ability to have language. But what about language itself? Once the capacity is there, how does language continue to change? Because it clearly does, right? English today isn't Shakespeare's English.
Absolutely. This shifts the focus completely. Now we're looking at the evolution of language forms, sounds, words, grammar rules, once the biological machinery is in place. And linguists increasingly see this as a kind of competition. Different ways of saying things, different grammatical structures are constantly vying for dominance within a speech community.
Like linguistic natural selection.
Pretty much. And just like in biology, there are 2 main mechanisms driving these changes: drift and selection.
Okay, explain those in language terms.
Drift is change happening just by random chance, pure stochasticity. Imagine someone mishears a word slightly, or a few influential speakers happen to prefer one pronunciation by accident. Over time, even without any real advantage, that variant might just randomly take over, especially in smaller groups.
So change for no real reason.
Exactly. Whereas selection is driven by actual differences. One form might be easier to say or clearer, or maybe it carries social prestige, sounds cooler, more modern. There's an intrinsic preference pushing it forward.
And how do linguists tell the difference? Because a change might look like it was selected for, even if it was just drift, right? You mentioned S-curves.
That's the big trap. The neutral Wright-Fisher model, borrowed from population genetics, is the baseline. It assumes only drift. But drift alone can produce those nice S-shaped curves where one variant replaces another.
Ah, so you see an S-curve and think, aha, selection. But it could just be random noise.
Precisely. You can't just eyeball it. You need rigorous statistics to actually test if the observed change is faster or more directed than you'd expect from random drift alone.
Which brings us to the FIT, the frequency increment test.
Exactly. The FIT is a statistical tool designed specifically for this. It compares the actual frequency changes of linguistic form over time against what drift alone would predict. If the real change is significantly different, usually significantly faster or more consistently directional, then you can reject the drift-only hypothesis and infer that selection was involved. It gives us a way to actually quantify these forces.
Okay, let's make this concrete. Real examples for English. Past tense verbs, like spill. It used to be spilled, now spilled is common.
That feels like simplification, right?
Right.
Regularizing irregular verbs. Makes sense?
That's the common sense explanation, yeah. The economy principle language should get easier, simpler. So researchers looked at 36 common irregular verbs in American English over about 200 years using huge text databases.
Did they all regularize?
Here's the shocker. Using the FIT, they found clear evidence of selection, rejecting drift, for 6 verbs. But, get this, 4 of those 6 showed selection away from the regular form, towards irregularity.
Wait, what? Like which ones?
Like dived, increasingly becoming dove, waked, becoming woke, lighted, becoming lit, and sneaked, becoming snuck. Only 2 showed selection for the regular form.
So snuck isn't just like bad grammar, it was actively selected for.
The data suggests selection played a role in its rise, yeah. It completely flips the script on language always simplifying. Sometimes, maybe for reasons of emphasis or distinctiveness, we collectively select for more irregular, complex forms. Mind blown. Okay, what about another big one? Using do in questions and negatives. Did you eat instead of ate you? I do not eat instead of I eat not.
Yeah.
That feels fundamental now.
Totally fundamental. Researchers tracked this change from the 1400s to the 1900s,
Hmm.
and they found a really interesting mixed story. For questions, interrogatives like, did you ask? Huh, the rise of do was actually consistent with neutral drift. It might have just started as a random variation that happened to catch on by chance.
Huh. So it wasn't necessarily better at first for
Maybe
questions.
not inherently, according to this analysis, it just spread. But here's the twist. For negative statements like Mary did not eat, and for commands like do not go,
Yeah.
the change was strongly driven by selection. The FIT rejected drift decisively.
So drift started it in one corner, then selection grabbed it and ran with it everywhere else.
That's the implication. Maybe Jado drifted into questions, became more common, and then its presence created a pressure maybe for grammatical consistency or clarity or reducing ambiguity that led to selection favoring its spread into negatives and imperatives. Chance provides the variation, selection locks it in and expands it. A really neat interaction.
That is elegant. Okay, one more famous one, Jesperson's cycle. The way English negation changed over centuries.
Yes. From the Old English style, ich ne sais, I not say, to Middle English, I ne say not, that double negative.
Right.
And then eventually losing the need to get I say not, which was standard before do took over fully.
So that whole cycle, drift or selection.
Selection, clearly, at each major step, both the shift to the double negative need not and the later shift to just not after the verb showed strong evidence of selection when tested with the FET.
Why? What was the selective pressure?
The linguistic theory, which this data supports, is about emphasis. Speakers tend to want to make negation really clear, maybe more emphatic, so they add things like adding not to the existing ne. But then that new emphatic form becomes common, normal, loses its punch.
So speakers find a new way to be emphatic, maybe dropping the old ne and just stressing the not.
Exactly. It's this cyclical drive for emphasis and clarity, with selection pushing each stage forward.
Fascinating. Okay, zooming out a bit, how does word frequency fit into all this? It's always seemed like common words be, have, go change less than rare words. Why?
That's a classic observation in linguistics. And the traditional explanation is usually selection again. Specifically, purifying selection. Meaning that because common words are used so much, any errors or variations that crop up get corrected really quickly by the community. There's strong pressure to keep them stable because they're so important for basic communication. Selection purifies them, keeps them correct.
Makes sense. But this new research offers another angle, right? Using drift.
Exactly. It doesn't necessarily replace the selection idea, but it adds a really important layer. They argue that common words simply experience less random drift.
How does that work? Less randomness for common words.
Think about it. If a word is used thousands of times a day by millions of people, the chances of a random error or a weird personal quirk actually spreading and taking hold are much, much lower than for a word used only occasionally by a few people.
Like ripples in a huge pond versus a small puddle. The big pond smooths out disturbances faster.
That's a great analogy. More usage means less stochasticity, less random fluctuation in its form being passed on. It's just statistically less likely to drift off course.
Did they find evidence for that?
They did. They found a significant link between how frequent a verb was and a statistical parameter in their models called N, which basically represents the effective population size influencing the word, essentially how much drift it's subject to. Higher frequency meant a higher N, which means less drift.
Wow. Okay. So it's not necessarily just that common words are actively protected by selection, but also that they're inherently more stable just due to sheer usage numbers reducing the impact of random chance.
Precisely. It's likely both forces are at play, but it adds this crucial role for drift, or rather, the lack of drift, in explaining stability.
So what's the big takeaway from combining frequency with drift and selection? How should we think about language change now?
It means we should expect different mechanisms to dominate for different words. Changes in rare words might often be driven by random drift they're flying under the radar, less constrained. But changes in common words are more likely to be the result of selection pressures, either purifying selection, keeping them stable, or directional selection, pushing them towards forms that are maybe easier, clearer, or, as we saw, sometimes even more irregular if that serves some expressive function. It paints a much more dynamic and nuanced picture of language evolution in action.
What an absolutely incredible journey we've taken today. Seriously, from just distinguishing language and speech
Which is crucial.
To the amazing story of our vocal tract. I mean, the idea that our low larynx might have started just to sound big and scary.
Yeah, the size exaggeration idea. It's
Right.
compelling.
Long before it got hijacked for
Yeah.
talking. And then the brain's role, the mirror neurons linking action understanding to potentially understanding language.
Providing that foundation for shared meaning, for parity.
And then seeing how language itself is still evolving, this constant dance between random chance drift and these selective pressures pushing things towards regularity, or sometimes, surprisingly, irregularity.
It really underscores that language isn't just some static tool we invented. It's deeply biological, rooted in our evolutionary past, and it's alive, constantly being shaped by forces similar to those that shape species.
Every single sentence we speak is kind of an echo of that deep history and a participant in its future changes.
Beautifully put, yeah.
So here's a final thought to leave everyone with. We've talked about deep historical change, but think about right now. Communication tech is evolving at warp speed: social media, AI, instant global chat.
Mm-hmm. Totally new environments for language.
Are we seeing new kinds of drift, maybe super fast drift, happening online? Or new selective pressures like optimizing language for algorithms or character limits? How might understanding these deep evolutionary forces, drift, selection, pre-adaptation, help us think about, say, creating AI that can communicate in a truly human, adaptive way? Or even about the future of human language itself in this digital age?
That's the big question, isn't it? What will communication look like centuries from now, given these ancient forces meeting brand new technologies? Makes you wonder.